welcome to the second lesson of my course. So, I'm not saying this time good morning, good afternoon, or whatever, because I don't know, so I'm just saying hi. So, I hope you're doing well and that you are ready for this second lecture. So, today we are finally going, recall that last time, I'm not going to say yesterday because I don't know when you watched the video, but last time we introduced the concept of valuation, absolute value, and we started to play a little bit with it, and we already proved two main results, the product formula and the degree formula, right? So that was the thing that we saw last time. So, today we are going to define, finally, the main tool that we use in Diophantine geometry, that is height. So today we're going to see the definition of height. And we're going to try to motivate a little bit why they are important and which kind of arithmetic information they carry on. Okay, so for today, the title of the lecture of today, 2, is going to be height in projective spaces. So, I hope you know what is a projective space. Anyway, I'm giving the definition, don't worry, just in case you are not familiar with it. But, somehow, yeah, I'm going to assume that you already know this concept, so I'm just going to recall the definition. So, actually for the next lecture, what I'm going to do is like a recall about projective spaces, abelian varieties, in projective spaces, abelian varieties as a particular case. So, this is not really related with Diophantine geometry, but they are objects that we are going to use. So, next lecture, I'm really going to take the time to define all those concepts. So, just in case you don't know them. So, in case you know them, then you can skip the next lecture. But, today, at least for the first definitions, I don't really need you to know what is a variety. So I'm just going to work on the general projective space, okay? So, maybe I can mention that for today, in case you want to check another reference to complete the things that I'm saying or to look at the same things but explained in a different way. So, I'm really following section B2 in the book by Andri and Silverman. Or, again, this is like a classical thing, so, you can find many good references in which you have all those definitions. So you can, as I said, follow this reference, or why not, you can use also section 1.5 in the other reference that I gave you. So, again, in the online platform, you are going to find the notes for my course. So, again, I cannot really call them my notes because they are very, very inspired on these two books. So, it's not really that I produce them. I'm really following those books. But, in those notes, you can find the references for these two books, and you can find some extra links with information. So, I encourage you to look at the notes, even if you're going to find really, the things that I'm just explaining here. So let's go with the definition. So, we start by taking a point in a projective space. So I'm just going to recall what we understand by a projective space. So, for the moment and for the first example and motivation, I'm getting the point to be a rational point. But later on, we are going to consider projective spaces with the coordinates in a bigger field, like in a number field, okay? So it's going to be a more general setting. But just right now, to motivate, let's start with the rationals. So this, we can see it as point or given by, be careful, even if there is an n, there are n plus 1 coordinates, because we start by 0. Okay, so we take this in here. So sorry, I was writing the field. So rational coordinate. So this is a point in here. Okay, but now the thing is that we consider this set up to equivalence given by an equivalence relation. What is this equivalent? So I mean, this set is the quotient of all those points by this relation. So basically we say that 2 points like this are related if and only if there exists lambda, another rational number, and different from 0, this is a way of saying it, it's an invertible element, such that actually the coordinates yi are just a multiple of the coordinate xi. So this defines an equivalence relation in here, and I mean we can consider the classes by these equivalent relations, and this is a projective space. But I mean, again, I'm sure that you already know this, so I mean this is just like a recall. Okay, so let's start by taking a point like this in here. So basically, because the points in here are defined up to proportion on their coordinates, because I mean these 2 points are equivalents, so I mean I can really take any lambda. So I can assume that P, that is a point in here, is given by some coordinates like this, okay, in such a way the coordinates are actually integers and not only rational numbers, right? Why can I do that? Well, I mean, I can do that because if I have a denominator in here, I can multiply all the coordinates by that denominator. So I can clean up denominators. So, I mean, even if it's a point in the projective space with rational coefficients, I can assume, and I do, that the coordinates are integers. And even I can ask something else. So I can ask the greatest common divisor of all the coordinates to be equal to 1. So I can ask for this, and for the greatest common divisor of all the coordinates to be equal to 1. Why? Because if it is not equal to 1, that means that there is a number that divides all coordinates. But then I can divide all coordinates by that, because I have this equivalent relation given by this proportion. So, I mean, I can assume that I'm in this setting, okay? So, P with integer coordinates and with greatest common divisor equal to 1. Okay, so now in this setting, I'm going to define finally the height of the point P. The height of P is 8 of P equal to the maximum of the absolute values. So if I don't say anything, is the standard one, so the Archimedean one in Q. So this is going to be, I mean, now I'm going to generalize this definition, of course, to a more general setting. But this is a definition of the height of a point in a projective space. So somehow it is intuitive, right? I mean, if I want to measure how big is a point, what I do is that I just look at all the coordinates, and I look at the absolute value of those coordinates, the classical one, and I take the biggest one. So I can say that the point has that height. Okay, now I'm ready to give you the general definition. So, I mean, I hope at least that you agree with me that this is like kind of a natural definition for the height of a point when it is defined over the rational numbers, and then I can do all these things about assuming the coordinates are integers and they are coprime and blah, blah, blah. So, I mean, I hope that you find this reasonable and a good motivation to now give you the more general definition of what is a height. So, definition. Let K be a number field and P a point in the projective space with coordinates in the field. Then I'm going to define two heights. So the first one is called multiplicative. You will see why. It's natural to call it in this way. So the multiplicative height and the logarithm height are defined as follows. So, first thing, here I am writing in the notation the field K. This is going to be important because actually the definition is going to define of the field, on the field. We'll see later how to remove this dependency, okay? So this is by definition equal to the product. When the product runs through all the evaluations for the field of the maximum, so basically I'm getting the motivation that I gave here, and this time let me take the normalized absolute value, so of this thing. So this is the first definition for the multiplicative height. Notice, first remark, if I take K to be the field of rational numbers, then this thing is going to be equal to this thing, okay? Why? Okay, this why I'm going to tell you later. There are factors that cancel, and this we are going to prove it in a real proposition. But I mean, this agrees with what we have there. Okay, so this one is the multiplicative height, and now I'm going to define the logarithm height, small h k of p, equal actually, and this is why the name, to the logarithm of the multiplicative height. And this, we can write it, if you want, as follows. So now, because I'm taking a logarithm, the product becomes a sum. So this is equal to minus mv minimum of valuation of the coordinates. Okay? What I did here, I mean, I just take the logarithm here. Okay, but recall that actually we had that in general this is equal to this, to the local degree, so it's the local degree that comes up here, and that here it was equal, so I mean we had the evaluation, right? So this was equal to, well, I mean if it was a p-adic thing, this is equal to p minus the order of x at p, and the evaluation was coming from here. Or, I mean, if you want, it's easier if I write it the other way around, actually. That we defined b of x equal to minus the logarithm of this. Right? So, I mean, this minus logarithm is the one that appears, this logarithm with the norm here, the exponent goes down, and this minus is this minus. So, I mean, this is just a different way of rewriting it. Okay, very well. So, this is the definition. Let's look closer now at some properties of this object that we have just defined. And, I mean, why this agrees with the thing that I wrote here. We'll see that in the special case in which the field K is the rationals. Okay, so lem let K be a number field, so same setting, and P a point in the projective space, then the following conditions hold. So the first one is that the height is actually well defined, because, I mean, we gave that definition, but actually somehow this defines that depends on the choice of the coordinates for P. So, I mean, actually we are going to prove that it doesn't matter which choice of coordinates you make. If you use the formula that I gave for the definition of the height, you get the same thing. So, is independent of the choice of homogeneous coordinates So this is the first thing. The second thing is that it is actually bounded, like lower bounded. So it is always greater or equal than 1 for all P in the projective space. And the third condition, and actually this is what is going to measure this dependency with the field. If K prime is a finite extension of K, then there is a relation between the height of the point P over K and over K prime. And actually this relation is precisely this one. So they are almost the same thing, except that here I have an exponent coming up. So the degree of the field extension K prime over K appears here. So we have the relations between the heights. Okay, so let's prove it. Okay, so let's start with the first one. So assume that we decide to write P as follows. So yeah, maybe I'm going to call it lambda, okay? So I took another choice of coordinates, of homogeneous coordinates for the point P. So let's see which is the value of the height for this point when I take these other coordinates. Okay, so then it's K of P is equal to the product when I take all the evaluations in MK of the maximum of this. Sorry, lambda. Right, but now I can use that the absolute values are multiplicative ones. So actually I can take out the lambdas that I have here. So I can write this as the product when V is in here of the norm of lambda times the product when V is in here, right, of the maximum of the norms of the X. Okay, now the term that I have here is actually the definition for the height of P when I take the coordinates x0, x1, xn, so without the lambda, without the multiple. But what is the thing that I have here? This is just the product formula that we saw yesterday, well, the other day, that we saw during the last lecture. So this is equal to 1. So this is equal to 1 because of the product formula that we saw in the previous lecture. So basically what I got here is that this is equal to the height of P with the coordinates x0, x1 to xn. So basically we get what we want, that independently on the choice of coordinates that you do of the point P, you get the same height. So it is well defined. This is the first thing. Okay, very well. So now we can prove the other two. So, I mean, the second one actually is very easy now that we proved the first one. Why? Because actually we can take P. So for the second one, take the coordinates of P in such a way that some xi is equal to 1. Right? This I can do it. The only thing that I have to do is just divide. For instance, imagine that x0 is different from 0. So I can just divide everything by x0. And then I'm going to get the first coordinate equal to 1. So, okay, if I have one coordinate that is equal to 1, then I just look at the formula for the height. So, I mean, I can look at the formula here. So, I mean, each time that I'm taking the maximum here, I have at least 1, 1. So, I mean, this maximum is going to be greater or equal than 1. And I do the product of all those numbers, that they are all of them greater or equal than 1, and hence the height is greater or equal than 1. So in this situation, we have that this is greater or equal than 1, and we are done. Easy. Now, the third one, the third point. So we want to check this. And actually, this is going to be, again, a consequence of the other main result that we saw last time. So, I mean, we have just used the product formula, and now we're going to use the degree formula, and it's going to give us this. So, actually, the only thing that you have to notice is that this is equal to this product, right? To the maximum. So let me write it in this shorter version. Okay, so this is equal to this, but this, we can split it as the product, like this, right? So, I mean, those are the valuations in K, and those are the valuations that divide B, okay? Of the same thing. Right? But now what is happening? What is this? The relation of this, this is equal, if you want, to the valuation WV, and here we have the local degree, right? And I mean, we want to relate this one with the local degree of B instead of the local degree of WV, right? So let me call it, let's see how to call it. So we want to relate this, let me write it in the other way around. Right? So this is this height, and this is equal to this. Right? And this actually is the same thing like this, because W restricted to K is equal to B, because W divides B, right? So the only things that we have to relate now are those degrees and those degrees, right? But now we have the degree formula, right? That tells you that the sum of NWV divides this is equal to the degree of K prime over K. So if you want, I use it twice, the degree formula, first to see it as K prime over Q, and then to K over Q, right? So, I mean, we can deduce this from the degree formula. So, I mean, by using this relation, and by using that here we have those exponents, right? So we get that this is equal to HK P to the degree of K prime K, right? Because I do the sum through all the W that divides B, right? So yeah, maybe this I suggest you to do the computations by hand to really check all the qualities that I said here. So is this just a consequence of the degree formula? And with this, we get the third condition on the lemma. So now I can prove the thing that we said at the beginning, that actually, if the field that we take is the field of the rationals, and if we take P with integer coordinates, and such that the greatest common divisor of all the coordinates is equal to 1, then the height, so I can write a Q if you want, because it depends on the field, this is equal to the maximum of the standard classical absolute values of the coordinates. Why is this true? So, I mean, actually, this is an exercise that is in the list of exercises that you have to do, but I want to motivate a little bit why, because this is going to be the motivation that why it's good to use this height. So, I mean, the idea is as follows, and it's like, okay, so the definition really, so I mean, here is the definition. You have to go through the product of all the evaluations, right? So you can do, I mean, you have that the greatest common divisor of all the coordinates is 1, which means that when I look at a non-Archimedean valuation, so a p-adic valuation corresponding to the prime p, there is at least one coordinate that is not a multiple of p, because I have that the greatest common divisor is equal to 1. But then the maximum that appears here for a p-adic valuation is going to be equal to 1, right? Because for that coordinate, you get that the valuation is 0. So you get that the absolute value is equal to 1. Whilst for the others, if there is a p that divides, then you are going to get that the absolute value is p to the minus something, but this is smaller or equal than 1. So, I mean, here the maximum, when you get a p-adic valuation, is always equal to 1. Okay? So those terms, they don't give you anything. So we only have to look at the non-Archimedean valuation. So what it is a non-Archimedean valuation? It's the standard one. I mean, it's the one that comes from the classical absolute value. That is this one. And actually, this is the only terms that appear here. But I mean, this is true because I asked the coordinate to be integer and because this is important condition. Okay? But then, I mean, during the lemma, the first point, we already proved that actually it doesn't matter which choice of coordinate you do. But I mean, of course, for this formula to hold, you need to get those in this way. Okay, so I mean, this is the idea, if you want, this is the motivation. The definition of the height of a point in the projective space over the field K is motivated by the fact that you want to imitate the definition of the height that you give over the rationals. So you want to give something that doesn't depend on the homogeneous coordinates, so this is why you use all the evaluations, okay? And then you want something that somehow measures like this absolute value, okay? Well, I mean, I don't know. I hope that I motivated that this is an important thing to do. Okay, very well. So now, what is the next step? So, I mean, after this last equality that we proved here, because right now we have defined a height that defines on the field of definition, so we can try to define something that doesn't depend on the field of definition, right? Because even if I take a point with rational coordinate, you could assume that those coordinates are in a bigger field. So, I mean, which height do you use? The height for k or for k prime or for k? So we are going to give something that doesn't define on the field. So definition, the absolute, so I mean this absolute means that it doesn't depend on the field. The absolute height in the projective space, Pn, well, actually I'm going to say it in plural because I'm going to say it for the multiplicative one and the logarithmic one. So the absolute heights in Pn are defined as 8 of P is equal to 8k of P to the 1 divided by the degree of k over q. So this thing now with this factor is independent of the field k that you consider. And this is because the last property that we proved in the previous lemma. Okay, so this is going to be the multiplicative height. So now in a natural way, we can define the logarithmic height as the logarithm of this one, right? So we have 8 of P equal to the logarithm of 8 of P. So if you want to see the dependency of this height with the hk, just notice that this is equal to this. So again, it is just an extra factor that we have here that depends on the field in such a way that makes that this product is independent of the field, and we can define this logarithmic height. Okay, so I think that is the moment to do an example, right? Because maybe you are getting lost with all those heights. Okay. Maybe just before the example, a small remark, a very small one. So we have defined those heights for points on projective spaces. So we can use them to define actually the height of a point in a field. So just let me remark this, right? If I have alpha k in here, then I can consider this as in P1, and now I can define the height of alpha equal to the height of this point in P1. So, I mean, with this, I just want to mean that actually I define the height for a point in a projective space, but you can use this definition just to define the height of a number without looking at it inside a projective space, okay? Okay, so now, example. So I'm going to take a point, P, given by those coordinates. So this is in P3. And if you want, the field is this complicated field. Well, complicated. Degree 4 field, right? I mean, this is a number field that is extension of the rationals. Okay, so let's take this point and let's compute what is the height. So the first thing is I already took this point with one coordinate equal to 1, right? And I don't have denominators. So somehow I put it myself in the nice setting that we had in the example where the rational numbers. Why I'm saying that this is a nice setting? Actually now I can compute, look. I'm going to take first all the evaluations. So B is a evaluation on MK, and K is the field that I have here, okay? So I'm going to look at all the evaluations that devise a prime number P, okay? So I want to compute the contribution to the height of those evaluations. So again, this is equal to the maximum of the coordinates of my point, so let me call it xi, corresponding to 3. So I have this. But actually, because I have one coordinate that is equal to 1, corresponding to this coordinate, I'm always going to get here a 1. And corresponding to the other coordinates, depending on the order of the prime P dividing those numbers, I'm going to get P to the minus order of this number. That is something smaller or equal than 1. But I have this 1, so the maximum is going to be equal to 1. So all those factors are equal to 1. So basically, I just have to look now. Those are the Archimedean, the non-Archimedean valuations. So I have to look at the Archimedean ones. Those ones, they are denoted, well, like this. This is just, again, an abuse of notation. And I have to compute this. Okay, so now let's look at this closer. Which ones are those Archimedean valuations? So we know it, right? Because during the last lecture, we saw this proposition that described the Archimedean valuations. And basically, we know that we have to look at all the embeddings of this field into Q bar, right? So K into Q bar. So, and the ones that fix Q. So Q goes to Q. So basically, an embedding like this is determined by the image of I and square root of 3. So, I mean, because I have complex numbers inside this K, I have I, so K is not a real field, right? So, I mean, I have to look at those conjugate embeddings, and I mean, I can just take one of them. So I can always assume that I goes to I, right? Because the one that sends I to minus I is the conjugate one, but I can just take only one for each of those pairs. And then I have to see where do I send a square root of 3. And this can be sent to this one or to this one. So basically what I have, so recap. This degree is equal to 4, right? And the embeddings of K into Q, actually embeddings, they are 4 because the degree is equal to 4, so I have 4, but they are conjugated 1. So I have tau 1 conjugated, tau 2 conjugated. So I can assume that tau 1 is the one that sends I to I and square root of 3 to square root of 3, And tau 2 also sends I to I, but sends a square root of 3 to minus a square root of 3. So I'm going to have two Archimedean values, absolute values, that corresponds to these two embeddings, okay? I also know that the local degree has to be n tau I equal to 2. Why? Because the local degree of this one plus the local degree of this one has to be equal to the total degree, that is 4. So, okay, I agree that it could be, instead of 2 of them equal to 2, there can be 1 and 3, agreed? But actually we are not in that situation, because the local degree has to divide the global degree. So they have to be equal to, they have to be a divisor of 4. So both of them have to be equal to 2. Okay, so we are going to use this information and we are going to plug it here. So let's go back. So basically, I mean, I have those two embeddings. So this is going to be equal to the maximum of xi tau 1 square times the maximum of xi square tau. Okay. So, I mean, we have this equality, so this product, there are only two factors here, so this maximum and this maximum. So basically, we just need to look at the maximum of the absolute value that we have here. So, okay, very well, so which one are those absolute value? So we have to look at those numbers and look at the embeddings. And then we take the standard absolute value. So let's look first at tau 1. Okay, so tau 1, the embedding sends these to 1, these to 3 plus a square root of 3, because it goes with the same sign, 4 and 1 plus I. So, I mean, I just have to look at this, but what is this? Maybe I can rewrite this again. So, I mean, this without the 2 is actually, I'm going to write it. So, this is equal to tau of xi times the conjugate of this one and 1/2. So, I mean, this is the classical norm, right? So, I mean, this is this absolute value. We define it like this. But now I have to add the exponent, so I have a 2. But this 2 is going to cancel with this. So, actually, this is just this product, right? And now we have the same thing with the 2. So is this times the maximum. I'm going to erase here. So I mean, well, this you remember what I did. So I can erase. Oops. Times the maximum of tau 2 of xi times the conjugate one. Okay, so I mean, this is just the norm, the square of the usual norm, the Euclidean norm, if you want to put it in the complex numbers. So which ones are the norms? Okay, so the norm here is 1. Now I need to multiply this by the conjugate 1, but the conjugate 1 is itself, because this is a real number. So actually it's just the square of this number. This is 4, so you just take again a real number, the square, and this is 1 plus I, and the conjugate is 1 minus I. 1 plus I times 1 minus I is 2. 2 is smaller than the square of this one, and 1 is smaller than the square of this one, so we have to look at those ones. So recall that a square root of 3 is more or less 1.7, let's say. So this number is actually bigger than this number. So for the maximum, we get the square of this number. So this is equal, the first term, to this. And now we look at the second embedding. So recall that the second embedding sent a square root of 3 to minus a square root of 3. So actually now when we look at those products, here I get again a 1, but here I'm going to get 3 minus a square root of 3 square. The square is because, again, this is a real number, so the conjugated is the same number. then a 4 squared here, and then here 1 plus I times 1 minus I, but this is again 2 and it's smaller than this, so it doesn't contribute to the maximum. But now what is happening? Be careful. Now I'm looking at 3 minus a square root of 3. And this is a real number, still positive, but smaller than the 4. So this time, for this second term, is the 4 who wins. So I get a 4 squared. So we have computed in this way the height of the point P, because now for computing the height, we just have to do the product of all the things we computed here, but here we want all once, so this is the only important factor. So we have that 8k of P is equal to 3 plus the square root of 3 squared 4 squared. And now even we can compute the height without the k, so the absolute height. And for this, we gave the definition here. We just have to do the corresponding, not a square root, but the root with the degree corresponding to the field, and we have a 4. So we get 3 plus the square root of 3 divided by 1/2 and 1/2, but I mean actually this is equal to 2, right? Because this is the square root of 4. So this we can write it with a 2, and maybe it is nicer if I put it here. So we get this value for the height. So here is the height computed for an example. So maybe it's important to say now that actually I did all those computations by hand, and I mean they are kind of long, I mean, as you saw, even if it was like a small example, but actually we have something great. So, I mean, we can do it with a computer. So, I mean, you can use Magma. So, I don't know if you have heard about this program. So, I mean, in general, to have it, you have to pay for it. But actually, there is a free version on the internet. So, I mean, of course, because it is free, you cannot use it like for doing big computations, but you can use it for free for using computations that take less than 2 minutes. So, I mean, I'm not going to write here the website, but if you go through the notes that I prepared, you have a link, so you can directly go to the website. So, I mean, you can use here Magma, and you can do all these kind of computations with the computer, so without having to do them by hand. So you can, for instance, double check as an exercise that I computed this right. So, I mean, you can use, so there is a documentation in the website, so I mean you can get there like the commands for computing like the different things, but just let me present like the command that you can use here. So you can compute, you can use the following command. That is, so it's important to use the capitals, so be careful. Height on ambient P, comma. So, I mean, by using this command in Magma, you can compute the height of all the points that you want. Okay, so this is good for the example. Now let's go to see more properties of these points and on this height. Okay, so we are going to prove now a proposition that relates the height of that relates the height of a point and the height of a conjugate point. So, I mean, I guess that maybe you already guess what is the solution for this. Proposition. The height of the conjugate of a point is actually equal to the height of the point. So, for all sigma in the Galois group of k over k. So, we have this equality here. Okay, let's prove it. This is easy, actually. Proof. So, the idea is the following. So, I mean, when I get one element, sigma, in the Galois group, basically what I'm giving, so I mean, this sigma is an embedding, right? But sigma in particular, so I'm going to write more space here. So it's something like this, right? I mean, it's just an embedding. This is one of the embeddings that we were talking before. But I can be more precise. I can also see it as an isomorphism in the image, right? This on one side. And on the other side, I can also see sigma as something inducing an isomorphism between the absolute values for the field K and the absolute values for the field sigma K induced by this. So the conjugated field. I mean, eventually this may be K, right? I mean, if K is Galois, then we have the equality. This is equal to K. Sigma of K is equal to K. But maybe it is not Galois. So, I mean, it may be a different field, right? But this induces an isomorphism between the evaluations, right? Just by making the composition with sigma in here. Very well. So then we can write things as follows. The height of the conjugate of the point, right, as a point with entries in sigma of K, it is, by definition, the product when I take an absolute value in here of the maximum sigma xi So, I mean, this exponent is coming because here I took the normal, the absolute value, not the normalized one. And I have a valuation here. So, I mean, this is just the absolute value that corresponds to that valuation. And, I mean, the coordinates of the point P are the conjugated of the coordinates of P, right? So, I mean, this is just by definition. Very well. And now we can rewrite this as follows. So the product, but this time I'm going to get valuations in here. And I'm going to use this isomorphism, right? So I'm going to describe each valuation in here as its preimage by sigma of a valuation in here, right? So I can rewrite this as the maximum of the absolute value. Well, I write it and then I say it. Right? I mean, the only change is that instead of writing W, where W is a valuation for sigma K, I wrote it at sigma of V, where V is a valuation of K. So this is because this is isomorphism, right? And now this is equal to the product, so this is the same thing. Maximum of what? So this MV is this MV, right? So it's the same thing. And this XE comes from here. And this is precisely because of the isomorphism that we have here and the isomorphism that we have here, right? What is the meaning of that? This is precisely this, right? So this is equal to the height K of P. And now, of course, the absolute height, we just have to put this to the right exponent, but the degree of K and the degree of sigma K is the same one, so we get the qualities of height that we had here. And the result is proved. Okay, very well. Now, after this, I mean, we are ready actually to prove a very deep theorem. So, I mean, I'm happy that we can see the proof. There is actually a theorem that has very important consequences and that it tells us about the points of finite height. So, I mean, the idea is that we are going to start to see the interest of height and how they measure the arithmetic on the points. So, well, we'll see. I'm going to state the theorem. So, theorem for any b and d greater or equal than 0, the set of points on the projective space, So this is the algebraic closure of the rationals, such that the height of the point is smaller or equal than the bound. So I mean, I'm looking for points of a small height, and such that the degree, I'm going to explain the notation here, is smaller or equal than d, is finite. So what is it? What is this? Actually, this is the field. So we take the rational numbers and we add all the coordinates of the point P. So this is going to give us a number field, a field extension. So we look at the degree of this. So basically, this theorem is telling that if you fix the degree of the extension over which the point is defined, then there is a finite number of points of bounded height. So somehow the height of a point is something that grows, so that you can really like order the points on the projective space by the height. So I mean, this is somehow the meaning, and this is the interest of the height. So the height allows you, this is the idea, allows you to make a list of the points in a projective space. So you can say, okay, I take all my points with height smaller than 2. So I'm going to get a finite number of points, so I can really write them and have a list. Now I want to look at points of higher height. Okay, so I get some more points that I can add to my list, a finite number. So I mean, this is the interest of the height, and I mean, we are going to use it for this, to order and to try to, well, you will see, I'm going too far. Okay, let's see how to prove this theorem. So proof. Take P with coordinates, as always, like this, right? And we can make some with some of them equal to 1. So this is a trick that we already applied before, right? Then we have that the maximum of the norms, of the normalized absolute value, is greater or equal than the maximum of this and 1, right? Because one of the coordinates is equal to 1. So in this set, there is at least a 1. So we can write this in this way. So it's greater or equal than this. Okay, this is the first observation. And then this observation implies that then the height of a point P, so recall this height, I mean, it's just the product of all those terms. When you do the product that runs through all the absolute values. So you want to do, this is the product of all those things, and all those things are greater or equal than this, right? But this is precisely the height, the terms that appear if you just look at the height of each coordinate. So this is greater or equal than the height of each coordinate, right? Very well. Now I'm going to fix a D in here. Because, I mean, in order to prove that this is finite, I'm going to prove that this set is finite, where here this is equal to D, a small d, for each d in this interval, right? This would imply the result. So I'm going to take such a d, I'm going to fix it now, and I'm going to prove that that set is finite. Very well. So, okay, let now x be an algebraic number of degree d, right? And I can take its conjugate. So if x has degree d, it has d conjugate. Well, I mean, in particular, one of those is actually equal to x, right? And all the other ones are the other conjugates. So I have this d conjugate. So now I can take its minimal polynomial, right? let f the x, so I'm going to call the variable t, equal to the product of t minus xi, the conjugate ones, right? So this is the minimal polynomial. But I can also write it as follows with symmetric functions. T d minus r, so let be its minimal polynomial. Okay, so the minimal polynomial, we know that the roots are the conjugate ones, so this I wrote it with the corresponding coefficients, so of course r here goes from 0 to d, right? Those are the symmetric functions, and yeah. So now what we are going to do is that we are going to look, so I mean I can tell you this is a strategy, so basically we want to bound the height of the point, so what we want is to bound the coefficients of the polynomial defining the point, well, its coordinate. Okay, so I keep with the proof here, I keep going. Okay, so notice now, I mean for each of those coefficients, so I'm going to look at the absolute value of those coefficients, right? So I'm going to write them explicitly. So this is the sum 1 a1 until ar t of x a1 xir, right? I mean this is a symmetric function of order r. So I mean here this is just an equality. I just wrote it by definition. This is less or equal, so now I'm going to write this constant explicitly to say who it is, times the maximum, so again the a1 ir less or equal than d of this. Okay, so what did I do here? What I used was a triangle inequality, but many times, because here we have many factors, right? How many factors do we have here? Actually, we have d over n, right? So the different choices of i's there. So, I mean, I have to choose r elements between then elements, among d elements. So this is a combinatorial number, d over r. And I mean, I have all those many terms, and now I use the triangle inequality, and I get this with a constant here. But actually, this is the thing. So this constant is going to depend if the valuation is Archimedean or non-Archimedean, because in the Archimedean case, we have in the non-Archimedean case, we have the ultrametric inequality. So we can get even like a higher constant here. So basically, this constant is going to be equal to d over r, that is in general always smaller or equal than 2d if the valuation is Archimedean. And I can directly write 1 if it's not, because then it is non-Archimedean, and then we have the ultrametric inequality, right? So, I mean, anyway, this is a explicit constant. This is important thing, okay? Okay, and now I can keep going, and this thing is smaller or equal than CVRT, and now I'm going to write, this time, the maximum of XERB, right? Because this thing, I always have the same number of terms, R, that is the R that I have here, and each of these xi is smaller or equal than the maximum of this one. So I can rewrite it like this. Okay, and now we leave it this like this for a moment. We are going to use it later. Let me go further. So now I want to look at the maximum of all those coefficients. So, I mean, I wrote this for SR, and now I'm going to look at the maximum of all of these, right? So, like this. So, this is smaller or equal, and I'm going to put here something that is a constant, and it doesn't depend on R anymore, right? Because I have all of them here. So, who is this constant? Actually, I have that those numbers are always less or equal than 2 to the d. So, I mean, I, for instance, can take this equal to 2 to the d. So, actually, in this way, it doesn't depend on v and it doesn't depend on d. If v is Archimedean, not Archimedean, I could take a 1. But, I mean, this 2 to the d works always, right? So, this is smaller or equal than this constant that corresponds to this constant and the maximum of those things. So, here the maximum is when r is equal to d. Right? That is the greatest exponent that I have. So this is smaller or equal than this. So this maximum, 1, and a d. Oh, sorry, I forget here the maximum. Right? Okay, very well. Hard work. So we have this. And now, because I have this, right, I can define. So, I mean, this is for all valuations, right? So now I can do the product of these equalities, both sides, when I go through all the valuations. So this gives me in particular here the height of all these coefficients if I see them as a projective point. So the height of this is less or equal than 2 to the d that comes from this constant, and the product now, so here again I'm doing the product through all the valuations, so it's really the height of this number that I'm taking, and then I have here the d, so I get here a d, right? Okay, but now recall, this is the previous result that we proved. Who are the xi? So the xi, they were the conjugated numbers of the x that we took at the beginning. But we just proved in previous proposition that the height of conjugate numbers is equal. All of them are equal. So this number is actually equal to this thing. Sorry, x. D and another d, so d squared. Right? Okay. But now what is happening, because I mean, this height is bounded, right? I mean, we say that x was a point of bounded height. So this is smaller or equal than this. And d is also bounded, right? Because for us, d was 2 to the d was smaller than this. Okay. So now we worked so hard to get this inequality. How do we have to understand this inequality? So basically, we have to understand it that if we have a point, x, with a bounded height and with bounded degree, then the height of the coefficients of its minimal polynomial is bounded, okay? But those coefficients are rational numbers. Right? Because they are the coefficients of the polynomials. So they are rational numbers. They are just 7 divided by 3, 5, 1. And what happened with the height of a rational number that we know that is bounded? That there are only a finite number of rational numbers, right? Because which one is the height of rational numbers? I mean, it is just the maximum of the numerator and the denominator of the rational number. So if we are bounding that height, we are bounding the possibilities. So now we use that they are a finite number of rational numbers with bounded height plus this bound to conclude that we get a finite number of minimal polynomials with points with bounded height and degree, and then we get in total a finite number of those points in the set that we had in the theorem in here. Okay, so we did a lot of work proving this theorem, but now we can get nice corollaries. This is always a good thing, right? When you make a big effort for proving a theorem, but then you get like many corollaries for free. So let's start with the corollaries. So maybe I should leave, I'm going to leave here the statement of the theorem, so you can see how it implies the corollaries. Oops. Okay, so first corollary, and actually it has a name, so it is an important one, that is actually called Kroneker's theorem, and we are going to prove it as a corollary of this theorem. Let K be a number field and let P a point in the projective space with coordinates in K. So fix a coordinate I such that it is different from 0. Then we have that the height of P is equal to 1 if and only if, so this is a characterization of the points with height equal to 1, if and only if all those quotients, that they are well defined because I really asked this coordinate to be different from 0, each of these quotients is a root of unity or 0 for all G. So maybe you don't see directly why this is a consequence of the theorem, but I'm going to add like a 2 lines proof and we'll see it. But I mean, this is amazing, right? I mean, we have an explicit, very precise characterizations of points with height 1. Somehow this is intuitive, right? Because we said that the intuition behind is that the height of the point is somehow like the maximum of the absolute value of the norms of the coordinates, more or less. Right? So if we have that the height is equal to 1, that means that each coordinate has valuation 1. And the only numbers with height equal to 1 are the root of unity. More or less, right? This is intuition. Well, let's prove it. So proof. Sorry, I didn't get the right paper. So, okay, so we have P that is given by those coordinates. So the idea is that I define PR, so another point started by this one, so and this one, and we have that the height is equal to 1, right? So now I'm going to define this one. Okay, so it's the point for which I took for each coordinate the power r of each coordinate of P. Okay, so because the height is multiplicative, then I get that the height of this point is also equal to 1, right? But now we proved that there is only, so if I take here b equal to 1 and I control the degree, so there is only a finite number, and I mean the field of definition, the coordinates of these points are in the same field that I have here. So I'm fixing the degree extension. So there is only a finite number of such points. So what is the only possibility for having here only a finite number of points when I vary r? So I mean, if you want x, each coordinate, so let's look at the first one. If you want this to produce only a finite number of values, the only explanation is that or this is equal to 0, or this is equal to a root of unity, because then at some power is going to be equal to 1 and then it's going to be periodic. So here is how this theorem implies this corollary. So maybe you want me to write it. So we have this, but there is only a finite number of points of height equal to 1. So then implies that the xi has to be, as is written here, root of unity or 0. Okay? Very well, so this is the first corollary. Let's go to the second corollary. The second corollary is an immediate one, so no proof. I mean, it's really a corollary. No need of a proof. And again, it's a very important result because it also has a name. Corollary. So, Norcross theorem. They are, so I mean, this is a little bit, I mean, before I'm writing it, it's a little bit a generalization of the result that we used before. So we said that over the rational numbers, so I mean, I'm just looking at rational numbers, if I fix a height, there is only a finite number of points, right? Because, I mean, the height of a rational number is like the maximum of the numerator and the denominator. The classical absolute value is this maximum. So, I mean, of course, if I'm bounding what you can put in the denominator and what you can put in the numerator, sorry, the other way around, numerator, then you get a finite number of options. But this is over the rational numbers. So now Norcross theorem is the equivalent result, but for number fields. So there are only finitely many algebraic integers of bounded degree and bounded height. Well, I said that I was not going to write a proof. I'm going to do it. It's just one line. How do we get this result from what we did? So, I mean, the idea, again, is that if you have a number here, the way of defining the height is that you see this number in here. Right? And now you just apply the theorem, and you know that you have here a finite number of points of bounding degree and height. So we are done. So this is the other important result that we have proved today. Okay, so I'm just going to finish for today with the next theorem. So it's a theorem that starts to play a little bit more with the geometry, right? Because we have defined this height for points in a projective space, but now, well, I mean, you can imagine that what we want to do at some point is define the height for points in varieties. So if I want to define the height of a point in a variety, I have to see this variety inside a projective space. But maybe I can see this variety inside a projective space in different ways. So somehow I will need to relate these different heights depending on those embeddings. So I mean, we'll see this with more details in 2 lectures. But before doing that, I mean, I'm going to need the following. Okay, so we are going to see like this theorem that allows to relate the height on different projective spaces. So let me state the theorem. So we take a rational map. So I'm going to write explicitly the coordinates. So be a rational map of degree t. Defined, so I mean I can consider it directly defined over the algebraic closure of the rationals even. So I don't need to fix a number field. So what is the meaning of degree d? So let's look at it closer. So basically I have here a projective space of dimension n, and I have here a projective space of dimension m, and the degree is d. So this means that actually it is given by n plus 1 polynomials if each of them of degree d and they are homogeneous one in n plus 1 variables. Okay? So, okay, this is the setting. Now I'm going even to take, let's set in P to the n. So, I mean, this is the starting projective space. Be the subset of common zeros of all the coordinates. Okay? So, I mean, basically this means, if you want, that this morphism is well defined outside set. So set is what it is not well defined, right? Because set is the set of points in which all of those are equal to 0, so the morphism is not defined. Okay, so phi is defined on Pn not set. Okay, so under those hypotheses, I mean, I'm sorry, I have no more space here, I have to move. We have the following results. First, the height associated to the image is smaller or equal than d time. So remember, this was the degree of the morphism. The height of the starting point plus I need to add a constant here. But this constant is, I mean, it doesn't depend on the point. So, okay, it depends on the morphism, phi, it depends on n, m if you want. But once that you fix the morphism, then it doesn't depend on the point. So we have a constant there. And now, second point, even more, if P is not in set, so remember that set was this set in which the morphism is not really well defined. So if we take the point not to be in set, so maybe I can write it better like this. So in Pn not set, so the morphism is well defined, then it's not only that we have this inequality, what happens is that actually we have an equality. So basically it means that the height of the point is up to the degree of the morphism, the same one that the height of the image of the point. So we can relate the height of the point on one side and the other side of the morphism. So I mean, this theorem is really important. We are going to use it a lot. So proof, let's see it. So I'm actually only going to prove this inequality. So in order to prove the equality here, we will need to also prove the inequality in the other sense. So I mean, this one involves like so many computations. It's not difficult. So I mean, I'm just giving to you like a reference in case you want to check it in the note. And I mean, let's see this one. That I mean, this is the one that use like nice ideas that can be used later. Okay, let's see how to prove it. So we start by writing explicitly the Fi defining the morphism. So, I mean, this is going to be equal to a sum like this. So, some abuse of notation here, actually E is a multivalued index. So, I mean, when I'm writing here, recall that this is not X neither. This is a compact way of writing the n plus 1 variables that we have, because we start with points on Pn, okay? And so, yeah, maybe I don't know if this is too clear, but I mean, X really means x0, xn, so all the possibilities for the variables, and E is actually a multi-index. right? So when we write x to the e, really what we mean is this product. Okay, so this is just an abbreviated form of doing it. And say that the norm of e is equal to d is that we want the sum of these exponents to be equal to d, right? Because f has degree d. Okay, so we start by writing this like this. So actually, how many terms do I have here? It has, so this is a combinatorial exercise that I leave to you. So it has at most, assuming all those coefficients are different from 0, n plus d over n terms. Okay, on the other hand, given a point, is valuation here is actually the maximum. So this you can take as a notation, because I'm going to use this. Because I'm going to write like big formulas, so they are going to look nicer if I use this shorter notation. And then I'm going to define the norm of f, again, as the maximum of its coefficients. And finally, I'm going to use this notation that, I mean, this is going to be similar to the constants that appear in the previous proof. So, I mean, it depends. This is going to be equal to R if B is Archimedean, and 1 if it is not. Okay, so again, this is a constant that is going to come up from the triangular inequality. And in the non-Archimedean case, we can even use the ultrametric inequality, so we can get a higher constant. So, I mean, this is why we're going to use this constant. Okay, so I need another remark. I mean, once that I define these constants, we actually have that the norm, or the absolute value of the sum of R terms is smaller or equal than this. Right? I mean, this is because of the triangular, again, triangular inequality or the ultrametric equality. Okay, so now I'm going to use all those ingredients, okay, in some formulas. Okay. So, I mean, it's a lot of notation, but you will see. It's going to make things easier now. Okay, so let's start with the following observation. So, I mean, we want to relate the height of the image of the point with the height of the point, right? So, I'm going to start to look at the height of the coordinate. So, I mean, if I take P, the image of P is made of coordinates that they are given by this Fi, right? So, I'm going to look at the height of each of the coordinates of the image. Okay. So, this is equal by definition to this. I mean, I'm just rewriting F in the way I wrote it there, so with this fancy notation. So, I mean, this is just by definition. Okay, but now I'm going to use the inequality that I saw before with this fancy constant that we introduced. So, this is the constant, because we have here, we said n plus d over n terms, so it's a constant associated to this number of terms, times the maximum of each of the terms that we have here. But because the norm is multiplicative, I can write this as follows. Right? Because the absolute value is multiplicative. So I can take the absolute value of this product, but this is the product of this with the product of this. Okay, and now this is smaller or equal. So I have the constant, so this is the same thing. And now this is precisely what I defined to be the norm of Fi, right? And now I can change this. This E is smaller or equal than, I mean, the sum is D. So I can change this, is the same trick we also saw before, by the maximum of the absolute value of each of the coordinates to the D, right? But this, notice, so we have these constants, we have this, and actually this thing that we have here is actually equal to this. Right? This is the D, and this is the norm of the P. So now we are in the good way, right? Because the height of the point P is the product of all these things when I consider all the valuations, and the height of the image of the point is again the product of these when I consider all the valuations. So now that I have this inequality, I'm going to do the product through all the valuations. And, well, then I'm going to take the right exponents. So what I get is that the height of phi of P is less or equal than this constant, but this constant is less or equal than this. It could be directly equal to 1, right, in the non-Archimedean case, but, well, in general it's smaller or equal than all these. And, I mean, this is something that only depends, this is something that only depends on 5, right? And actually is what we can call this thing, this is by definition, if you want, the height of the morphism phi that is related to the height of each of the coordinates. But this doesn't depend on the point. It only depends on the morphism we started with. And this is, of course, the height of the point. Okay, so we get something like this. So now I'm going to take logarithms of this expression. And then we get that the logarithm height is less or equal. So for the logarithm, this thing goes down. This is a constant. That is something that we add. D times h of P plus h of phi plus the logarithm n plus the n. And all this thing is the constant that doesn't depend on the point that we call O of 1. So, I mean, so we're done. We have the inequality, the first one. The second one, as I said, I leave it to you if you want to check in the references. But, I mean, we did even something else, because we proved this inequality, but this constant, we can compute it explicitly. So, I mean, we are going to use this result many times, like this inequality, even an equality, right? I mean, with the second part. So we are going to use a lot this in the future to prove that there are things that they are bounded. But, I mean, don't forget, this is very useful when you want to do explicit computations, that actually the constant is explicit. So you can explicitly compute it for its case. Of course, it depends on the morphism, but you can compute it. Okay, very well. So I think that is enough for today. So we are finishing here with this lecture. So see you for the next one.